SanDisk, this 32 gigabit RAN chip. So we mentioned this design in the RAN lecture, and this is from this paper. I think they have an ISCC version in 2013 and the TSSC journal paper in 2014. So here are the specs for this design. So it's a very like 3DX point, but with RAN instead of phase change. And it's a crossbar, a 2-layer, and the middle layer is a shared bit LAN, and you have the selector and the RAN in this stack. So this is a cross-sectional view of the chip, and here is on the top interconnect you have those RAN cells. So here, if you look at the spec, the read latency 40 microseconds is pretty slow. If we talk about RAN, actually at the cell level, if you at the device level, the RAN read can be fast, like tens of nanoseconds. But when you integrate into the chip, the latency becomes like a microsecond. So this is question. When I first read this paper, this is the question I have. So we can look at the organization of this chip and then understand why it's like this better. So one thing we need to notice is that although here this RAN, let's say this crossbar pitch is 40 nanometer and half pitch is like only 20 nanometer. So basically here each is like 20 nanometer. You can see that the transistor underneath on the substrate is a huge transistor. So you see here, this, for example, this is one transistor, contact to contact pitch. Probably you see here is like, I don't know, maybe 200 nanometer already. So SanDisk didn't disclose what technology they use for the CMOS, for the transistor. They only say that the RAN is 20 nanometer RAN. That means the RAN cell size is 20 nanometer. They didn't say what CMOS node on the substrate is used. So I can suspect this is like old technology node, like 180 maybe.
Sorry, Professor, they're referring to 130. That's 137 millimeter.
Yeah, they didn't say, I don't know. Yeah. So we can suspect maybe 130, 180 nanometer. So this will explain why the circuit performance is not as good as expected. Although the memory is very dense, but the transistor is very large, very big. So this is just one transistor, and then you need to have like a 20 transistor for the SenSamp. Then you can imagine the SenSamp is very large compared to the memory array.
Do you think the larger transistor is just for the higher current requirement, or for?
I don't know. So I think they just do this at an older technology node. Yeah, for this particular design. So this is the organization. Total capacity 32 gigabits, and they have 16 they call bay. So essentially, it's the highest level like block or bank. It has 16 bay or bank, and within each bank, it has like 32 times 4, 128 blocks. You can think the block is one subarray, and within one block, it's a large crossbar array. It's like 2 kilo bit LAN times 4 kilo VLAN, and you have 2 layers. So that is the number of cells in one block. So here it says that each bay has 64 SenSamp, but you see that each bay actually has 128 blocks. So only 64 SenSamp within this one block. Sorry, one bay. So that means each block That means the SRAM is shared between the blocks. So you have maybe one block here will only have one SA. This is because, as we discussed earlier, the memory is very dense, while the transistor is very large in this case. So probably this one subarray in the peripheral circuits area can only put one. You can only put one SRAM there. So, but when you read the bits, probably you are going to read 64 bits from one block. 64 bits. So that means you have to borrow the SRAM from other blocks. So I think that's the reason why the speed is slow. Because you have to borrow the SRAM from other blocks, which means non-wire in between. So here is the SRAM design for this particular chip. And this is crossbar array, and it has the similar bias scheme as we discussed before to read. So essentially, you will apply read voltage. It's voltage mode sensing. You are going to apply the read voltage from here, from the read bias. You are going to have a read voltage to the bit line. And then I think they play with a little bit on this VUB signal, but you can think it's 0, ground. If you do that, then you have the read voltage here, read voltage along the bit line. But if this wire line is ground, then current will flow this way. So for the cross-point array, then you need to bias the other to be V-read because you don't want current flows here. So you are going to sense this current. This current is going to pull down the voltage of this node. And then this will become the node to be sensed. This will be compared with a reference voltage as input to a voltage mode SRAM. So if you look at the waveform, you will into pre-charge the bit line, and after that you are going to decay the bit line depending on the cell resistance. Strong cell means the resistance is small, so you will have large current to discharge the bit line, so it decays faster. And weak cell, it will decay slower. Then you can have a SRAM enable signal somewhere here. If you enable a SRAM here, so you can differentiate the on and off of strong and weak cell. Because the voltage difference, one is above the reference, one is below the reference. So you have the different polarity compared to the reference. Then the voltage mode SRAM can tell you the output 0 or 1. Okay, so this is SanDisk design. And the last part of this lecture is to give you a tutorial with this NV-Scene simulator. So why do we need this kind of simulator? So this is to estimate the circuit level performance for your memory design, like the metrics such as area, latency, read or write, energy, read or write, and leakage power. So similar work have been performed for the SRAM or DRAM using this cacti, which was originally developed by the HP lab. So in this NV-Scene simulator, it extends the design from the SRAM DRAM to non-volatile memory including the flash and all the new memories like RAM, phase change, SDDM run. So this tool is developed by Professor Yuan Xue's group at UC Santa Barbara. I think he started this research even before he moved to UC Santa Barbara. He used to be at Penn State University. So this is a subarray in Naval Blocks we showed earlier, and this simulator tried to model the individual blocks, the modules, the circuits, and then the memory cells. So it will provide different options because you may have very large design space. So you have many choices. Each module you will have different choices. For example, you can choose a transistor type. You have high performance transistor, low power transistor, low standby transistor. So this is more related to the foundry technology. And then you can have other design parameters like interconnect wire pitch, repeater design. This is a buffer for the interconnect. Sensor, as we discussed, you can choose voltage sensing, current sensing. And the driver, we discussed that you can optimize for area, optimize for latency. And the array, you can have this, they call it most accessed, essentially it's 1T1R, or crossbar. So you say you have so many design options, right? If you combine all of them, will be a huge design space. If each you have like a few options, then the total design space is, as a transistor type, you have 3, and the interconnect type you have 2, and sensor you have 2, and then you multiply those, will be like and also you have the array size. You can vary that. If you consider all the design space, will be like hundreds or even thousands combinations. So the goal to use this simulator is to run this simulation to see the trade-off between those metrics like area, latency for this whole design space. And I think this is some model validation with some chips. So here, this is from one paper. They validate their model projection with the actual chip data from this 64 megabit MRAM chip. So you see that the area, latency, they have some errors, like a few percent, but it's kind of close as this high level of simulator. Because this is not SPICE simulation, this is just a high level simulation.
But the data is from SPICE?
Not really.
Then
So,
where are the data originated from?
So they built the analytical equations for all the modules. So for the inverter, they have the analytical equations for the delay for one inverter. So it's not SPICE simulation. So for the wires, it's RC delay. For the energy, if it's dynamic energy for the wire, it's CV square. Right? So it's all based on equations, analytical equations. So if you use this NVSyn, you can do this practice. So for example, your goal here is to design a most accessed RAM, basically 1T1R RAM for the last level cache. So this is your design goal. You want to design this at 32 nanometer, and your total capacity is 8 megabyte for this cache. And then you can have different design targets, right? Then you will end up with different design options here. You can optimize the design for area, latency, or the leakage. So here are the options you may have in the NVSyn. I will skip that. So you have different options for different modules as we discussed. So I just want to show you the results if you use this simulator to run the example we showed earlier. You want to design this 8 megabyte RAM cache. So you will have different kinds of data points. Each point corresponds to one particular combination of your modules. And you can plot this as the latency versus density for different 1T1R RAM or crossbar RAM, or you can have different kinds of SRAM design. So you will see that they have some trade-offs as you expect. Okay. So here, for example, this is to optimize for different targets. If you want to optimize for the area, you can get the smallest area as this number for this 8 megabyte RAM. And then if you want to achieve that, then your latency may be long. And if you want to achieve that, this is the option you need to use. You need to use cross-point array. You need to use this kind of large 512 by 512 subarray size. And then you want to use share the sensing. The sensing is external. And then the sensing type is current mode in. So the driver buffer should be area optimized. So here you can see that for different targets, you can have different choices for each module. And if you want to optimize for latency, then you can reduce your read latency to 1.7 nanoseconds. But then the array size will be smaller, and you need to use H-tree routing, and so on. So basically, this helps you to choose options if you want to optimize for some targets. And this is at circuit level. So typically for the computer architecture community, they will take this output from this MVC simulator and then run the system level benchmark to do the cache application. So for example here, this is a system benchmark. They will run it in this Gem5. If you take computer architecture courses, I don't know if Georgia Tech teaches Gem5 or not, but in other schools I know they will use Gem5 for the computer architecture course. So basically it's a cycle-accurate simulator for the CPU, and with workloads, different workloads. And here this is the design spec. So for example, you can define the clock frequency, and then L1, L2, L3 cache, you can have different options, SRAM or RRAM different capacity. And then the SRAM, RRAM parameters, like the latency, area, energy, will be calculated by the MVC. You use MVC's output as input to the Gem5. So if you do that, okay, you run the Gem5. So the Gem5's output will be the IPC, instruction per cycle, which is a metric to evaluate how you perform in those workloads. Of course, higher IPC, better. So here you can see that the designs with all SRAM here, this is the pure SRAM, L1, L2, L3. Then you will have the best IPC. And if you use all RRAM, then the IPC is low. However, the power is lower if you use RRAM, area is lower if you use RRAM. This is as expected, right? So SRAM is still the fastest. So if you use RRAM, then the performance will degrade, but you can save the area or power from this result. Of course, RRAM is not good choice for cache. Okay, to start with, this is just a practice. Okay. Because there's one thing they didn't consider here. Do you know what is missing in this study? Why RRAM is not good choice for cache?
Not embedded in the chip.
Speed.
No, you have your homework. You just did. Yeah, exactly. So endurance, right? So there's no endurance considered here. So cache you need to very frequently write, so RRAM endurance not good enough. Okay, so this is a tool, and I put the version in the folder of the your homework folder. You can download that and compile or I think in any Linux system you can run it. So time is up, so I will skip the tutorial. Maybe you can do it next class. So basically I will show you some of the format in this simulator, so you can use that and you can understand better. You can do this.